So let us take up the analysis of rigid plane frames. Here also we assume each member of this rigid plane frame to be axially rigid, so that the member flexibility can be taken similar to V, that is L by 6 2 minus 1 2. If it is not axially rigid, then this L by EA term to be introduced. So it is not 2 by 2 matrix, it will be a 3 by 3 matrix with this L by EA also placed coming into picture in the member flexibility matrix. That's all. It is a combination of that truss member and the B member. That is, if it is axially not rigid. So we will take up that axially rigid, that's only all the members similar to B member. So now straight away let us take an example of a rigid plane frame and see that. Again, the analysis can be done by following that 8 steps. Of course, that last step is in finding the final element moments. That's all. So let us pick up this rigid plane frame. So let us take this frame ABCD and analyze it by this flexibility method. So as I told, the same step to be followed. First step, you have to identify the independent forces at the ends of each element with element coordinates. As I already told, so each element is assumed to be axially rigid. That means the end moments we can take it as the unknown independent force, like that. That is your element coordinate. That is 1 star, 2 star, 3 star, 4 star. This is 5 and 6. All clockwise direction taken as positive. This is the element coordinates. Similar to B, the element coordinates. That is the member end moments to be determined during analysis. So this is what we have to determine. The end moments corresponding to these 6 coordinates of this frame we have taken the positive direction. That's the first step. Identify the independent forces at the ends of each element which we have to determine during analysis. That's the first step. So that means we have to determine this PM, which is nothing corresponding to these 6 coordinates. PM1, PM2, PM3, PM4, PM5, PM6. Transpose. Because it's a column vector, I am writing it as transpose. So the next step, second step, you have to find the degree of static indeterminacy and make the structure determinate by releasing forces equal to degree of indeterminacy. Here, it is a rigid plane frame. Degree of static indeterminacy is given by 3m plus or minus 3j, where m is the number of members, that is 3 members, 1, 2, 3. this is first member, second member, third member, or third element. So M is 3, R is number of support reactions, so it is fixed here, 3 reactions, hinge, it is 2 reactions, so 3 plus 2, 5. And J is the number of joints, 4 joints are there, so minus 3 into 4. So this is 9 plus 5, 14 minus 12, it is equal to 2. Degree of external indeterminacy or minus 3, that is 5 minus 3 equals 2. Therefore, degree of internal indeterminacy is 0. So hence, this given structure is externally indeterminate to the degree 2. That means 2 of the external reactions you can release so that it becomes determinate. So let us choose the reactions. Let us choose the reactions, that is external reactions, at support D, at support D as redundants, So that means here we have 2 reactions, that I will remove it. That means inject support, I will remove it so that it becomes a cantilever type of frame which fixed at one end. So the basic determinate structure, it will be like this. This end becomes free end. So A, B, C, D. So the reactions removed are vertical reaction here and horizontal reaction. This is coordinate 1, this is coordinate 2. The reactions which I have removed, their positive directions are indicated by the coordinates. That is what the second step says. Find the degree of static indeterminacy, which is 2, and make the structure determinate. So I made this structure determinate by removing hindered support and identify the coordinates of redundants removed. That is 1 and 2. Or the forces which has been removed, that I have identified redundants with coordinates. So that means, so the redundant forces removed are is R1, R2 corresponding to this. So this is in global coordinates, this in local coordinates. All element and forces to be determined during analysis, they are in local coordinates, and all redundants, they are chosen in the global direction. So this is the first step. What is that we have to determine? Ultimately, after the analysis, we have to determine the final element and forces as well as these redundants. Last step is finding the redundants, so that this is evaluated. From this 8th step, it is evaluation of this, that in the 10th step. So these are the first 2 steps. So that is over. The first 2 steps are completed. Next, 3rd step, you have to develop the unassembled flexibility matrix. So because we have chosen for each element 1, 2, 3, the end forces, independent forces as the moments at the ends. So with reference to this, the member flexibility is given by L by 6CI 2 minus 1 minus 1, 2. So therefore, this member flexibility for member 1 and that is equal to member 2 because the length of the member AB as well as EI value, it is same as member BC because it's also 2 EI 6 meters, 2 EI 6 meters. So therefore, the member flexibility of these two members has to be same, that is equal to L by 6EI, that is L is 6 meters, 6EI, 6 into EI is 2EI, so 6 into 2EI, it becomes 12EI into 2 minus 1 minus 1, 2. That's what I take. L by 2EI, 2 minus 1 minus 1. Or this is nothing but 1 over 2EI, 2 minus 1 minus 1, 2. Similarly, member 3, FM3, for this length is 3 meters, EI is EI itself, so therefore member flexibility will be 3 by, it is 6 EI into 2 minus 1 minus 1, 2. So this is also 1 over 2 EI, 2 minus 1 minus 1, 2. That is the member flexibility. That means here all flexibilities are same. Therefore, unassembled flexibility matrix of the structure, full structure as a whole, is you have to club or you have to combine all these flexibility matrix here in a leading diagonal. So that is equal to 1 over 2EI, member flexibility of first member 2 minus 1 minus 1, 2, and other two members 0. So here second member, it is 2 minus 1 minus 1, 2 along the diagonal, others 0. So third member along third position of the leading diagonal, it is 2 minus 1 minus 1, 2. This is the unassembled flexibility matrix. Develop the unassembled element member flexibility matrix for the entire structure. That is, I will combine individual member flexibilities and place it along the leading diagonal here, like this. Along that leading diagonal, the member flexibilities appear. That is called that unassembled member flexibility. So this step is over. Then fourth step, you have to find the force transformation. You have force transformation matrix you have to develop. That is fourth step, force transformation matrix. Force transformation matrix. So this force transformation matrix we obtain by applying unit load along the global coordinates chosen in step 2. That's what I have told. Whatever this is, I told you global coordinates, this is element coordinates. So by applying unit force along each of these global coordinates successively one by one and find the element coordinate forces. That is that force transformation matrix. So that means I have to apply in the basic determinant structure, of course. This is the basic determinant structure. First, I have to apply along the global coordinate a unit force. R1 is equal to 1 in the direction of R1. I have to apply, and then I have to apply unit force in the direction of second coordinate, that is R2 equals 1, and I have to evaluate the forces corresponding to the element coordinates 1 to 6. Here also along 1 to 6, what is the force which is going to be developed by applying these unit forces have to determine in the basic determinate structure. And that I have to arrange in matrix form, that is nothing but T. It's a very simple process. I have shown these forces. So since you have applied a unit force, if you take a section here, moment about the, because these are all the moments where to determine. First, I will determine moment about this section, which is 0, because this is the force acting along the axis. So this moment is 0. Again, when this is 0, this also will be 0. Next, I can take this is over. Next, I will take a section here. Moment about this section is 1 into x. When x is 0, it is 0. So that means this is again 0. When x is equal to 6 meters, because this is 6 meters, this section I have taken at a distance x from here, whatever moment which is there, that holds good from this to this end. So moment here is 1 into x, so it is 0. Here it is 1 into 6, that is 6. 6 applied moment is like this, resisting will be this way, that is 1 into 6. 6 is the moment. So when this is clockwise, this has to be anti-clockwise because it is just on the other side. So that has to be equal. Next, here moment will be again 6. When 6 is here, here it should be opposite. So the same moment should be there. So like this we can determine, or as it is, because this is the applied load, so to keep this in equilibrium, there must be equal and opposite load here, and these two loads, sigma v equals 0 is satisfied, but this is upwards, this is downwards. Again it is not in equilibrium because it gives a moment. To keep this in equilibrium, there must be a moment, and that moment has to be developed here, which is in the clockwise direction. So this you can determine first as reaction, this, then when once this is like this, here it should be opposite, then here it should be opposite, then here it cannot go solidly. Either that way or by this way you can determine these moments. So that means the first column of your T matrix will be corresponding to element coordinate 1, it is positive 6. Here it is anti-clockwise direction, so it is minus 6. Here it is same direction 6. Here there are 0. So that is the first column of the T matrix. Next, this is over this. So the moment I applied a load here there cannot be any moment. So here this is 1 into this height, 3 meters. 1 into 3 is in anti-clockwise direction. So this has to be 3 like this. When this is 3, this has to be 3, clockwise, anti-clockwise. When this is anti-clockwise, here it has to be 3. Then, when this is clockwise, here it should be anti-clockwise. 3. Then, here, this is the force, so it gives a moment in clockwise direction, so this should be anti-clockwise. So this also anti-clockwise, this also anti-clockwise, mind it. So don't do this clockwise moment, because that's what actually I did earlier. Here, because the force is like this, horizontally, so it gives a moment in clockwise direction, that is 1 into 3 also it gives. So that's why this particular thing will go in this direction. So both are anti-clockwise moments. So the second column of this, it will be, this is minus 3, this is minus 3, this is plus 3, this is minus 3, this is plus 3, this is 0. So therefore, your transformation matrix T, that will be 6, minus 6, 6, 0, 0, 0. Then minus 3, minus 3, 3, minus 3, 3, 0. So this is a 6 by 2 matrix, and this is a 6 by 6 matrix. So I have developed the transformation matrix by finding the element member when forces, or by successively applying unit force in the direction of redundant. That's what I have told. I have just do exactly the same calculation. So this fourth step is done. So transformation matrix, it is generated. Then fifth step. So you have to determine the structure flexibility matrix. That by principle of contra gradients, we have derived that structure flexibility matrix as TT, FM, T. Both T and FM we have generated here. You can use it. So this is structure flexibility, matrix. That is Fs. That Fs is nothing but some principle of contra gradients. It is Tt into Fm into T. So that I have to determine. Both I have determined in this step 3 and 4, so I can use it. Therefore, this Fs is nothing but Tt. T is this, so Tt will be 6 minus 6, 6, 0, 0, and this is minus 3, minus 3, 3, minus 3, 3, 0. This is that Tt, transpose of this T matrix into Fm. Fm is 1 over 2ei, that is into 2 minus 1, minus 1, 2, then there is epsilon 0 here, then 0, 0, 0, 0, 2 minus 1, minus 1, 2. Likewise, the last two columns, I can write it 2 minus 1, minus 1, 2. That is Fm matrix. Into T. T is again this into T. That is 6 minus 6, 6, 0, 0, minus 3, minus 3, 3, minus 3, 3, 0. This is the T matrix. So this is 6 by 2 matrix, 6 by 6. First time multiply these two, it will give a 6 by 2 matrix after multiplication. So you will get this 1 over 2ei. So this 2 into this first row, I will multiply by first column. I will write it here. 2 into 6, 12, minus 1 into minus 6, it is plus 6, 12 plus 6 is 18. Next, second column, 2 into minus 3, minus 6 plus 3, it is 9. Then, minus second row, minus 1, 6, minus 6, minus 12, it is minus 18. Then plus 3, minus 6, it is minus 3. This is
plus
plus 3 minus 6.
minus
It is minus 3. Then third row 0, 0, 2 into 6, 12, other 0. It is 12. Then second column 0, 0, 6 plus 3, 9, 0. Then fourth column 0, 0, minus 6. Then others. Then minus 3, 0, 0, it is minus 3, minus 6, it is minus 9. Then fifth, 0, 0, 0, it is 0. Then second, 0, 0, 0, 0, this is 6. Then last row, this, it is again 0, this, it is minus 3. So this is that multiple of Fm and T, which is nothing but a 6 by 2 matrix. 6 by 2 matrix. So this again I have to multiply by Tt, 6 minus 6, 6, 0, 0, 0, minus 3, minus 3, 3, minus 3, 3, 0. That is that. Tt, FMT is this. So this is a 2 by 6 matrix. This is 6 by 2 matrix. This column equals row. Resulting will be a 2 by 2 matrix. This is 1 over 2 EI. It has to be a 2 by 2 matrix. So ultimately 2 by 2 matrix is nothing but our yes. So this is just a matrix multiplication, addition, that's all, nothing other than that. So this again here first row, first column. So this is 6 into 18, it is 108. Minus 6 into minus 18, it is 108. 6 into 12, that is 72. Then 0, 0. So this is 108, 216 plus 72, that is 288. That is the first row, first column. Then same first row, second column, that I have to enter here. So that is 6 into 9, 54, minus 6 into minus 3, 18, 6 into 9, 54, 0, 0, 0, that will be 126. Correct?
Yes.
126. Is it right? Just check. 6 into 9. I will just check that once. So I got the final result. I will write the final result itself. After dividing by 2 also, I will get 9 by EI, 60, 3 and 3, 5. So after doing that, this is what we are going to get. That is my FS, 2 by 2 matrix. So just check that calculation and do it. So the fifth step, it is done. That is how to find the structure flexibility matrix. Then you will take up sixth step. Sixth step is we have to determine this load matrix Dn after evaluating Pm. How to evaluate this Pm? So for this, I will take the basic determinate structure. This is the basic determinate structure which I got, and in this basic determinate structure, these are the loading, that is 50 kilonewton per meter, not 50, 25. 25 kilonewton per meter, 25 kilonewton per meter. Hitherto, I have not used the given loading at all. That I am using in this sixth step for computing this PM. So these are the loading, the basic determinate structure. So for the, because since it is this determinate structure, I can evaluate the reactions. I will analyze this. So the reaction here, it is total vertical load. So 25 into this is 6 meters. 6 meters, 25 into 6 should be this reaction, and this reaction should be 25 into this load, that is also 150 kilonewtons. 25 into 6, that should be like this, and the moment here, MA, applied moment due to the load is in the clockwise direction about the point A. Resistive moment should be in the anti-clockwise direction. So this entire moment which is going to be applied here from this member loading, it should be resisted by only this support, and this applied moment will be 25 into 6 into 3, that is 150 into 3, 450 for this load. For this load also 25 into 6 into 3, that's also 450. 450 plus 450, 900. So this should be 900 kilonewton meter. That is support reaction due to this load. Now for due to this, you find out these member end moments at all these points, as you did in other earlier steps, as you have done here by evaluating T. You can determine that will be your PM. This is exactly what you have to do. The basic determinate structure you can analyze and find the moments due to element coordinates. That is basic determinate structure element coordinates, and to that moment you have to add the moments due to least redundance. And the sum will give you the final member end moments. PM, the total final, that's all the analysis after evaluating redundancy. So here at this point corresponding to one coordinate, this moment is 900, and here at this point moment will be 900 like this, then due to this 150 into 6, that is also 900. That 900 cancels, then only due to this, it is 25 into 6 into 3, that is 450. This is the applied moment, so this will be 450 like this. When it is like this, here it should be the other way, this is 450. Then here of course it is 0, here 0, 0. If you go from here, so naturally, the PM star is equal to, that's what you have to determine. Find the structure of DL from this formula, TT, FM, PM star. The PM star you can evaluate in this fashion, either like this or by taking equivalent joint load, which you have done in P. So this is better, I think. So either one you can adopt. So therefore, this PM matrix will be PM1 is anti-clockwise minus 900. This is clockwise 450 PM. Then third, it is anti-clockwise 450. This is 0, 0, 0. So this is a 6x1 PM matrix. So now you can evaluate DL. DL is TT, FM, PM. That I read it. The continuation of that. So DL equals TT FM PM. So that is equal to TT is just now I have determined TT is 6 minus 6 minus 6 6 0 0 0 then minus 3 minus 3 3 minus 3 3 0. That is that TT. TT is this. FM is here you got that is 1 over 2vi into 2 minus 1 minus 1 2 0 then 0 this is 2 minus 1 minus 1 2 these are all zeros then last two columns it is 2 minus 1 minus 1 2 that is TT FM and P. P just now I determined here by taking that P body diagram of that basic determinate structure and evaluating the forces. So it is given by minus 900, 450, then minus 450, 0, 0, 0. So this is that TT, FM, PM. So this, if you simplify, that is, you multiply this and this, you will get, this is 6 by 6, 6 by 1, you will get a 6 by 1 matrix. Then that you have to multiply by is 2 by 6, that you will get a 2 by 1 matrix. The 2 by 1 matrix is nothing but your DL and that is given by 1 over EI 1 over EI minus 14,850 and minus 1550. So this if you simplify, you will get this final answer. So the moment you get this dn from this formula, that sixth step I completed. The last step I have to find the resultant. So that's all. So I will getting in that. Therefore, that last is seventh step. So sixth step is this. Seventh step to find or that redundant or is given by that formula Fs inverse multiplied by dj minus dl. That's what I have given. Or equals Fs inverse into dr. dr is nothing but dj minus dl. That's what I have taken. For dr I have substituted. That's the formula for finding this r. So the last step which I am doing that because I have evaluated all these. Fs inverse is nothing but Fs I evaluated there, that is 9 by EI 16335. So this inverse I have to find out. The inverse of this matrix is nothing but EI by 9 Instead of 9 by EI, that will be reversed. EI by 9 into determinant of that. Determinant of that is 16 into 580 minus 9, that is 71. 71, that is the determinant. Then cofactor of each of these. Cofactor of this is 5. Then cofactor of that 3 is minus 3. This is minus 3. This is 16. That is the inverse of that Fs matrix, whatever you have got here. Fs, that inverse, it is very simple process. 2 by 2 matrix, it can be inversed. And next, dj, of course there is no imposed boundary condition. There is no settlement of support or rotation of support given. So this dj externally it is 0. If it is given corresponding to these redundant forces, that value you have to substitute. So then it is only minus dl. Minus dl is here. That is nothing but 14, 8, 50, 13, 60. So minus, it is the minus of minus that will become plus. So that is that particular value. So if you simplify this, because it is a 2 by 2 matrix, this is 2 by 1, resulting will be a 2 by 1 matrix. That is your redundants R1, R2. This, if you simplify, you will get this as 100. This EI, because this is EI itself. I have not taken that. This is 1 over EI minus of that. So this EI cancel. So this side get minus 109.9 and this minus 35.9. So that is the redundant. So that means R1 is minus 109.9, R2 is minus 35.9. So that redundant forces R1, R2, that reaction set that hinges reagent is, you got it. The moment you got it, then you can evaluate that last step, evaluate the final forces. That's the last step. Of course, that I have not added into that general steps to be followed. So that, of course, then I have told that in the entrance problem, when I was doing it, so same thing we can do here also. That last step, that is the 8th step, to find final moment PM. That is whatever I have told in the first step to be determined. Second, all I have already determined. Now this PM is given by PM simply supported, which I have done. PM basic determinate structure. This is PM of basic determinate structure, whatever you have determined, plus that all value are the Tt into R. That's all. This is due to without redundant. Removing redundant, what all the moments develop due to given loading, then plus due to redundant, whatever you have determined, what are the forces. So that will give you the final end moments. This PM is nothing but your PM1, PM2, PM3, PM4, which I have told in the first step, PM5, PM6. These are the 6 member end forces to be determined during analysis. So that is nothing but simply supported moment. I have evaluated there. It is minus 900, then 450, minus 450, 0, 0, 0. Then this Tt is nothing but is 6 minus 6 zeros, then minus 3 minus 3
3,
3
3,
minus 3 0, that is dt multiplied by r, which you have determined in the last step 7 step, that is minus 109.9 and not minus 109.9, 109.9 plus this is minus 33.9. So this, if you simplify, you will get this final moment. So this is 2 by 6 matrix. This is
2, 1.
of course it is T. No, it is not T, it is T. I have to take this, sorry, it is T into R. T is 6 minus 6 0 0 minus 3 minus 3 minus 3 3
Minus 3.
3 minus 3.
Sorry, that.
Right?
Minus 3, minus 3,
So
3.
minus 3 minus 3
Plus 3.
This is plus 3 minus 3 plus 3 0 into this is correct. So this is what you have to take. It is not TT or it is TR. So this is a 2 by 6 matrix. Oh, it's correct what I did was okay. I did the mistake. So it is TTR only. What I wrote earlier is okay by writing. I got that mistake. This is 2 by 1. This will be
2 into 6.
okay, no? 6 by 2 it has to be because here column should be equal to row. So this 6 by 2 means it is T. Yes. 6 minus 6 0 minus 3 minus 3 3 minus 3. Yes, this is all right. This is 6 by 2 matrix. This is 2 by 1 matrix. So resulting will be a 6 by 1 matrix. So this also will be 6 by 1. So they are of same order. I can add it. So while adding, you will get this PM value which is also 6 by 1. So this final value I got. This will be minus 133.1 minus, then minus 101.4, then plus 101.4, then plus 101.7, then minus 101.7, then 0. After simplifying this and adding to this is plus Tm plus Tt T into R. T is this 6 by 2 matrix, R is 2 by 1. So resulting will be a 6 by 1 matrix. This also 6 by 1. If you add that, you will get a 6 by 1 matrix, which gives you value of PM1 to PM6. PM1 is this, PM2 is this, PM3 is this. So this you can use for drawing the final bending moment diagram. That's all. That is complete analysis of this rigid plane plate. So here, these are the body given, the analysis results, and these reactions we have determined R1, R2. So this is your R1, that is in the vertical direction itself, kilonewtons. This is opposite minus sign. So I have taken R2 direction like this, so it has to be reversed. So this is 35.9 kilonewtons, and I have determined the final moment. The two redundancies I have determined are, and these moments I have determined here. So first one, PM1, it is anti-clockwise, 133.1, then anti-clockwise, this is 101.4. So this next is positive, it is 101.5, 4. Next is 101.7 clockwise, 101.7, then 101.7 anti-clockwise. Anti-clockwise is like this. It is 101.7 minus, then here 0. Naturally, this is integer, so there won't be any moment that I got the answer. So these are the moment. Using this, we can plot the multi-point diagram as well as shear force diagram. With this, I have completed fully the rigid plane frame analysis. I have taken a rectangular frame with an equal leg. So you can try even with equal leg. So of course, that's all I have to consider all possible load cases. You can have a concentrated load here, concentrated load. Only that makes difference in computation of PM. If load is changed, that creates a change in that basic determinant structure analysis. But for that, there is nothing. And suppose if the rigid frame is this fixed here, then again you can make this free, so you have to introduce one more redundant R3, that moment. So due to that, you can develop T matrix. T matrix will be a 3x3 matrix, Fm, and R will be a 3x1 matrix, and you can develop the same kind of calculation you can do and arrive at the moment also, even if it is fixed. Maximum 3 redundance is ideal for hand computation. Remaining one extra, you have to switch over to the computer and get yourself training in usage of standard software for the analysis, because the software also has been written by following this direct the same steps, whatever has been indicated in mainly by stiffness method. So that procedure they are following, you can also do by the direct stiffness method. So next we will take up stiffness method of analysis. Same problem, that is stress, beam and this rigid plane frame. That same problems I will work by this stiffness method also, by transformation matrix approach. Then I will do direct stiffness method, which is mainly used for computers. So that also same problem I will work. Another 3 problems by transformation matrix approach, another 3 by direct stiffness. Totally the same 6 problems I will work in the next lectures. So that completes the syllabus. Thank you.